I hope I'm audible to everyone, right? So, good afternoon, everyone. Today I'll start with today we'll discuss about reduced row echelon matrix, and then we will talk about vector space, linear combinations, span, subspaces, and then subspaces means null space, column space, or range space, whatever. And then we will talk to you about basis. So before start, just a minute. Before start, I just want to ask, do you have any queries regarding today's course, today's lecture, or today's? I mean, I hope everyone have already uh, studied the video, already checked the video that already uploaded to the website. So if you have any queries, we can discuss, or rather we will start from the beginning. So I guess I'm assuming that you do not have any queries. So I just start with a row reduce or reduce row echelon matrix or row reduce echelon matrix.
And can we get the recording of previous session?
Sorry. Does anyone have any question?
सर वीक 1 में जो आपने सेशन लिया था उसका सर रिकॉर्डिंग
Uh, I'm sorry, your voice is breaking. I mean, could you please a little bit clearer or try to put your
सर
mouthpiece near
सर
to the.
वीक 1 का जो आपने प्रॉब्लम
हाँ, week
वीक
one का.
1 का
हाँ.
आपने जो प्रॉब्लम सॉल्विंग सेशन लिया था सर उसकी लिंक कहाँ पे है मतलब रिकॉर्डेड फॉर्म में अगर देखना
Week one ka link, I think that is shared with you. I mean, we have, I mean, I have already uploaded the link, that YouTube channel link in a Google Sheet, and that is
तो
basically you can check it on NPTEL. If you registered with your email ID password, then you can check that video link over there. I mean, let me just.
एक्चुअली आई डिडंट गेट इट सो दैट्स
Let me just.
if you could name the YouTube channel then I can search.
Actually, we are not allowed to mail anything to anyone because we just upload our video link and that Google Drive, whatever that that we had discussed over here is uploaded and go. I have already shared my YouTube video link and that Google Drive link. Okay, and how far I remember, just a minute. Let me check. You have joined that course, right? I mean, you have registered that course.
Yes sir.
Okay. So if you go there and there is a problem solving session, is there is a column called problem solving session, and in that problem solving session, I think if you click that, did you see there is a week 1, week 2, week 3, and then there is a problem solving session Jan 2025. Did you see that thing? If you click that problem solving session, you will see that click here to view the problem solving session lecture. You can see that video link over there. Is it visible to you? I mean,
But I didn't get the anything like problem solving
okay.
session.
I mean, Let me
Sir,
just
if you could share the
ah,
link in the
okay.
comment section, then we can.
Let me just show you. Let me just share. Let me just share that. Share my screen first. I just stop presenting right now and share this screen over here. Just a minute. My screen is visible to you, right? Right now?
Yes, sir.
Yeah. So, so if you go to that NPTEL session, if you go over there, you can see that problem solving session. Did you see?
Yes, sir.
Yeah. So if you
Yes.
click that problem solving session, you get this kind of page will come up, and then you have to click here. You will get this kind of thing. So that my name is Rudrashen that I have already, and this is my video link. There's another TA for this same course. So this is the video link that I have shared with you, and here is a drive link. Okay, so you can check that. You can get that.
Okay, sir.
You can get this thing all over here. Okay.
Okay, sir. Thanks.
So let's start with this. So we will start with row reduced matrix. So the first thing is we have reduced row echelon matrix. So in the previous class we have talked about only row echelon matrix. So row echelon matrix is something like that. So when we say that row echelon matrix, so it is something like, let's say a matrix A is a row echelon matrix. So it is something like that. We have a non-zero element. Let's say I'm considering that at the first row, the first element is non-zero, second element is non-zero, third element is zero, fourth element is zero. Doesn't care about, I don't basically care about the other thing. I just only care about the pivot element. So in that case, this is my pivot element. So as you know that this is my first pivot element. Pivot means that first non-zero element of the row is called pivot element, which is basically used to do the row operation process. So this is pivot element. Okay, and then what we talked about, like all the elements below this pivot element are zero. That has to be zero. Okay, so let's say the next pivot element comes at third column. Okay, it may comes at second column as well, but it should not be at the first column. So then this is my second pivot element. This is my second pivot element. In that way, you will get a echelon matrix. I'm not going to complete it, so you know that echelon matrix. So now, what is row echelon matrix? So, sorry, reduced row echelon matrix. So, reduced row echelon matrix says this is basically echelon matrix, and here the element below and above, should be zero. So, in case of reduced row echelon matrix, so reduced row echelon matrix is basically our pivot element should be 1. Okay, let's I call it B. So first of all, my pivot element should be 1. So here that pivot element is anything, any non-zero value. So I have to make it 1. So now our pivot element should be 1. Whatever the next element, I don't care. Whatever the next element, I don't care. Let's say this is 0. Now next pivot element comes at third column. Okay. So next pivot element comes at third column. That means we have to make this term to 0 as well. We have to make the element above the pivot column, above the pivot element, should be 0, and below the pivot element should also be 0. So if let's say in that case, our next pivot, obviously this is 0, this is 0, this should be 0, and let's say this is any non-zero value. The next pivot element, obviously we cannot get any pivot element over here. The next pivot element should be here. So this should be 1. So if this should be 1, then this term we have to make 0, and the last line is 0 over here. So if any square matrix, so this is basically a square matrix, 4 cross 4 matrix, right? So if any square matrix have all, if we get pivot elements at all row, or if we get a pivot elements at all row for any square matrix, the row reduced or reduced echelon, reduced row echelon form is become an identity matrix. So let's say if I have a matrix something like, so we'll start with some example. So I have a matrix something like A equals to 1, 1, 2, 3, 0, 0, double 4, 0, 0, 0, 0. So if you see this matrix already in row echelon form, okay, because there is a first pivot element, there is a second pivot element comes at third column. So obviously the third pivot element has to come at this fourth column, but there is a no pivot element, so the last element is 0. So we have to convert it into a reduced row echelon form. So what we have to do, the first thing we have to check the first element is 1 or not of a first row. So it is 1, we do not need to worry about this. Okay. Next is we have to change this second element. We have to change this element into 1. So what would be our approach? So R2 prime should be 1/4 R2, and what we will get 1, 1, 2, 3, 0, 0, 1, 1, and 0, 0, 0, 0. Next should be, we need to make this term, to 0, right? So we need to change the row 1. So row 1 should be row 1 minus 2 row 2. What we will get? We will get this, this. Right. So this is now my row reduce row echelon form. So that means very simple. You just have to make everything. You can interchange this operation. I mean, you can do the first, you can change the first row 1. You can first do this operation and then do this operation. It is absolutely fine. You just have to make it interchangeable. Okay. Based on that, what is your requirement? So, so this is basically row echelon form and reduced row echelon form. So we will check next thing. So, okay, I'll do this first, then I'll check. Next example, we have a matrix something like 1, 2, 2, 4, 6, 1, 2, 3, 6, 9, 0, 0, 1, 2, 3. So our approach should be, first we have to make this term, to 0, right? So what is R2 is R2 minus R1, and what we will get, we get 1, 0, 0, 2, 0, 0, 2, 1, 1, 4, 2, 2, and 6, 3, 3. And then we have to make this term to 0 as well, because we get a second pivot element over here. So what is our next approach? R1 prime is equals to R1 minus 2R2 1 2 2 4 6, sorry, 1 2 0 0 0, then 0 0 1 2 3, and here I am doing the next operation as well. R3 prime is equal to R3 minus R2. So, so this is our row reduced form. Now from here, this row echelon form or reduced row echelon form basically uh, it basically gives knowledge about the rank of a matrix. Now it is possible for a square matrix. If we have a square matrix, so it is possible to know the rank of a matrix. How we will know the what the matrix is I mean full rank or not? We just find out the determinant of that matrix, and we will get that if the determinant is non-zero, then our matrix is full rank. If determinant is zero, then matrix is not full rank. Okay, so it is very easier to understand what is the rank of a matrix from a square matrix. But if our matrix is not square one, it's if it is not square, it is a rectangular. Like this is a fat matrix, means the number of columns is more than the number of rows. So in that case, we cannot find, we are not able to find out any kind of determinant of any matrix, right? Because we do not know how to find out the determinant of a matrix of a rectangular matrix. So for that case, this row reduced form or row echelon form basically helps us to find out the matrix. So rank of a matrix. So how do we find out the rank of a matrix? The number of pivot elements basically decide the rank of a matrix. Now the proper definition of rank of a matrix is basically, so is basically number of linearly independent column of a matrix. So number of linearly independent column of a matrix is basically the rank of a matrix. So here the how many independent columns are there? So how many columns are there? Here basically 1, 2, 3, 4, 5, 5 columns. And independent columns means these columns and these columns, because these two columns have pivot in it. Other columns are basically the combination of these columns. So these three, these two are independent columns, and these three are three columns. Three column means we can easily make all these columns by the linear combination of these two columns, because if we say the second column is basically the twice of the first column, so basically the linear combination of first column. The fourth and fifth column basically the twice and the thrice of the third column. So basically they are the linear combination of the independent columns. So number of linearly independent columns of a matrix is basically known as the rank of a matrix. So if we need to find out a rank of any matrix, we have to check the how many independent columns are there, right? So if we have a matrix something like this, so we have matrix something like -1, sorry, 1, -1, 0, 0, -1, 2, -1, 0, 0, -1, 2, -1, 0, 0, -1. Okay. Now it's a first of all, the question is find the reduced row echelon form of A. Okay. And the second question is, what is rank of a rank of A? Okay. So we just need to copy this. Okay. So we have to do the find out the row reduced row echelon form. So first of all, R2 is basically R2 my plus R1, and we will get 1 minus 1 0 0 0. This is 1, this is -1, this is 0 0 minus 1 2 minus 1 0 minus. Okay, so then we will find out two operation I'm doing right here at the same time. Is R1 is basically R1 plus R2, and R3 is basically R3 plus R2. So what we will get, 1 0 0 0 0 1 min -1 0 0 0. This is 1, this is -1, and 0 0 -1 1. Okay, I'm doing then R2 is basically R2 plus R3. Yes, plus. Okay, and then just check if I'm doing anything wrong. Please stop me over there. Okay, R R4 basically R3 plus R4.
স্যার
Yes,
ଯୋଉ ଫାଷ୍ଟ ରୋରେ ଥାର୍ଡ କଲମଟା -1 ହବ।
first row. Which one?
ଥାର୍ଡ କଲମ
This one or this one?
R1 plus R2.
Okay, let me check. Okay, so R2 plus R1, right? So I'm doing changing R2 this. Okay, and then yes, sorry. No, not over here. Here is 0. Here. Here is right.
Yes, sir.
Yeah. Zero. This -1. 0 1 -1. I have to change R2 R2 means this is 0. This has to be 0. This is 0. 0, 0, 1, minus 1. Okay, and this is 0, 0, 0, 0. Again, I have to make an operation because I have to make this term as well 0 because I have a pivot element over here. I have a pivot element over here. I have a pivot element over here and over here. So we have to make sure that all the elements below the pivot elements are 0 and all the elements above the pivot elements are 0. So here I have to make this term to 0. Okay, this this term to 0. So that's why I have to make another row operation. I have to change r1 prime with the r1 plus r3, and then finally we will get 1 0 this 0 0 0 1 0 0. Sorry, I think I did a mistake over here. This should be -1. Yes. Yeah. Here should be -1, right? And then 0 0 1 minus 1 0 0 0 0. So this is my reduced row echelon form. So now from here, how many independent columns are there? We find that there are 3 independent columns. This is the one, this is second, and this is third. These 3 are the independent columns because all the pivot elements lie in this column, right? That's why these 3 are the independent columns. And this is the free column because we can, if we say, if we name these columns like v1 is basically 1, this v2 is basically 0 1 0 0, and v3 is basically 0 0 1 0. So we know that v4, which is basically -1 -1 -1 0, are basically -1 multiplied with v1 -1 multiplied with v1 plus -1 multiplied with v2 plus -1 multiplied with v3. So basically this is basically v4 is basically the linear combination of v1, v2 and v3. Means we can find the vector by combining, adding and scalar multiplication with any of the free independent columns. So that's why this column is called free column. So that means since we have a 3 pivot elements, that means we have a 3 independent column. That means rank of this matrix is basically, so rank of matrix A is basically 3. That means if you find out the determinant of this matrix, because we can find out the determinant of this matrix because this is a square matrix, 4 cross 4 matrix. This we can find out the determinant of this matrix. So if you find out the determinant of this matrix, you will get that the determinant is basically 0. We will not get any non-zero value. That means our matrix is not full rank. Full rank means if the length, since here the length of the matrix, since here the row and columns are m is basically equals to n, that means row equals to column. That means the highest rank that a matrix can achieve is basically 4, and we get that rank of the matrix is 3. That means we are not getting the highest value. So this is not a full rank matrix. So matrix A is not full rank matrix. Okay. So if a square matrix, if a rectangular matrix, for a rectangular matrix, let's say for a rectangular matrix m cross n, so m is not equals to n. Okay. So if m is less than n, that means number of rows are less than number of columns, like this one, number of rows are less than number of columns. So that means we have a fat matrix, right? This means number of rows less than number of columns. So we called this type of matrix is called fat matrix. Sometimes it's called fat matrix. Usually it is not, I mean, you will not get this kind of terminology in any book, but if you see any other lectures, so you will see that they sometimes calls it a fat matrix. Okay. Now, and if m is greater than n, that means number of rows is greater than number of columns. That means our matrix is something like tall one, tall matrix, something like that. Number of rows, let's say we have our three columns and multiple rows, let's say multiple rows. So this is something called tall matrix. So in that case, the maximum rank that a fat matrix can achieve, what is the maximum rank a fat matrix can achieve? That is the smallest value, that is m. Okay, so rank of a matrix is basically minimum, it's of m cross n matrix is basically minimum of m comma n. So whichever the value of is minimum, whether it's a row, it's a column, that will be the maximum rank that a matrix can achieve. So for fat matrix, the maximum rank a fat matrix can achieve is m, and for a tall matrix, the value should be n. So if for a fat matrix, if let's say we can find out we find out that the rank of a matrix is m, then we will call that matrix as a full rank matrix. Okay, because the maximum rank a matrix can achieve is m, and the rank of that matrix is also an m. We find after calculation we find out that rank of matrix is also an m for fat matrix. Then we call it a full rank matrix. But here in this case, in this example, the rank of a matrix is basically 3. Maximum rank that a matrix can achieve is basically 3. Okay, but here we get a only two pivot columns. That means the rank of this matrix is basically 2. That means the matrix is not a full rank matrix. Okay, so this is basically the concept of the rank of a matrix. Now, up to that point, I hope everything is clear to you. Now we will come to that null spaces and the solution of Ax equals to 0. Before that, we'll talk about the vector space.
Sir, basically these V1, V2 are matrices, then why do we call them vector?
Yes.
Sir,
Sorry.
in the previous question, V1, V2.
Huh.
Sir, they are matrices, right?
This is matrices. Matrices is basically combination of columns, or you can see these are basically combination of rows, right? So these are the column of a matrix, and we call each columns basically a vector, right? We just now when I will come to that that column space and null space or range space, sometimes called image space. So when I talk about this, this picture will also be clear. So matrix is basically what matrix is. Matrix is basically these are basically the equations system of equation and the coefficient in case of, because we are talking about the linear algebra, or if we talk about the real environment, like there is no complex number over there. So these are basically the coefficient of the variables, right? That we have already seen in the previous lecture, previous discussion, that these are the elements of matrices are basically the coefficient of the environment, a coefficient of the variables. So if I go back and sorry, so we see that this is basically the row picture and column picture we have seen, right? That these equation we can reform it in this matrix vector format, and these are the column. This first column always multiplied by x and the second column always multiplied by y. So these columns are basically individually is basically a vector which can spaces the particular space. So let me just discuss about what is vector space, and then I'll move to that column space and range space. Okay.
Yes, sir.
So first of all, I'll talk about vector space. So vector space is basically a space which is basically a collection of all the vectors, but they has to follow some certain rules. Okay, so those rules are basically if, let's say, uh, this is basically the shortest definition of vector space, something like that. If v1 and v2 belongs to a space v, let's say I'm assuming there is a some sort of space, some sort of vector space where v1 and v2 belongs there. If v1 and v2 belongs to that space, then alpha v1 plus beta v2 also belongs to this vector space v. So where alpha and beta are basically the real numbers. Okay. So basically the linear combination, if v1, v2 belongs some to space, belongs to some space, then the linear combination of v1, v2 has to be in that space. This is basically the shortest definition of vector space. But the longest definitions, basically there are certain axioms that each vector has to follow to make the space is a vector space. Okay. So the definition of vector space basically. So if x and y belongs to V, then following rules so first rule is x plus y should be equals to y plus x. This is the first thing, that if we add two vectors, I mean this is the associative law, x plus y should be equals to y plus x. Second rule is if if there exists z vector which belongs to V as well. So this sign, I hope you know this sign. So I'm just writing it over here. This sign means there exists, and this sign means belongs to. Okay. If there exists any third vector z, then x plus y plus z should equals to x plus y. First we add x plus y plus then we add z. It looks like very simple, but when I give you an example, you will see that in some cases these rules may not be followed. Okay. So now the third rule is there there exists a unique vector called zero vector. There exists a unique vector called zero vector such that x plus 0, any vector from that vector space plus 0, we will get the same vector. Okay, so if there is no for all x, if there is no such vector called 0 vector, then we cannot say that space is basically a vector space, because 0 vector has to be exist in a vector space. Fourth rule is basically there exists a unique vector, let's say minus x, such that x plus of minus x, we will get 0 vector. Okay, then fifth one, there exists a vector, there exists a scalar, sorry, 1, such that 1 times x equals to x. 6, c1 c2, c1 c2 are the two scalars, so should be equals to c1 multiplied with c2 x. So c1 and c2 belongs to R. So when I'm saying that this is belongs to R, that means these are the scalar. Okay, scalar. So first multiply c1 c2 and then multiply to the vector is has to be equal to the c1 multiplied with the c2 into x. This should be cleared. The seventh one is any scalar c multiplied with x plus y, that has to be equals to cx plus cy, and the eighth one, c1 plus c2 into x has to be equals to c1x plus c2y. So if these all 8 rule follows for particular vector space, then we call that space is basically a vector space. So which is basically similar to this one, which is basically in the shortest version, this is basically similar to this one, because alpha v1 plus alpha v2, so alpha and beta, alpha v1 plus beta v2, so alpha and beta could be anything, it could be negative, it could be 0, it could be positive number, anything. Okay, so that thing has to be there in the vector space. It could be fraction number, I'm not talking about. So when I'm talking about that belongs to real number, that means any negative, positive fraction number and 0 as well included over here. So this all 8 rules combined in this short format basically over here. If you check, then you will find out that this is the case. So I'm doing an example here. The first example.
So,
yes.
what is written in eighth point?
Eighth point. This one.
Yes,
this
sir.
one. So C1 plus
Yes, sir.
C2. Oh, sorry. This is my mistake. This should be X.
Yes, sir. Actually, I was confused.
Yeah.
Okay, sir. Clear.
So the example says, the question is, suppose I have a vector X, which is equals to X1 and X2. So I'm considering vector X belongs to some R2 space, and Y equals to Y1 comma Y2. Now it says that, next says that the addition, the vector addition is defined here in following fashion: vector addition and scalar multiplication. Sorry. And scalar multiplication uh, defined here in following fashion. fashion is x plus y, which is basically x1 plus x1 comma x2 plus y1 comma y2. This could be something like that, x1 plus y2 comma x2 plus y1. So this is the vector addition that question says that okay, this rule has to be followed. And the scalar multiplication, some scalar cx is equals to cx1 comma cx2. Now, sorry. So which of the following condition are not satisfied? So we have to check among these eight condition, which are the following condition that are not satisfied. If I'm saying that this is the vector addition and this is the scalar multiplication. Okay. So the first condition says, this is the first condition, x plus y equals, it should be y plus x. So I have to check that whether this x plus y is equal to y plus x is satisfied or not. So x plus y says it is something like x1 plus y2 and x2 plus y1. That means the first element of x added with the second element of y, and the second element of x added with the first element of y. Now if I do the y plus x, so this is something, right, according to this vector addition, according to this rule, I will get x plus y something like this, but y plus x something like this. So which means x plus y does not equals to y plus x, right? That means first condition is not satisfied. Let's check the second condition is satisfied or not. So I have a vector, let's say z.
So
Yes.
y
Yes.
plus x equals to y1 plus x2, comma
Yes.
y2 plus x1.
Yes. Oh, y2 plus x1. Yes. Yeah. Sorry. Now I have there is another vector, let's say z, which is z1 comma z2, because we are talking about the R2. So obviously z1 comma z2 would be the next vector. Now we have to check x plus y plus z. What is x plus y plus z? Something like x1 plus x1 comma x2, and this is added with y1 plus z2 and y2 plus z1, right? Now again I have to do the vector addition. That means first element added with the second element, that is x1 plus y2 plus z1 comma x2 plus y1 plus z2. Okay, and then condition is x plus y plus z. I have to check. So x plus y means x1 plus y2 and x2 plus y1, which is added with z1 plus, sorry, z1 comma z2, and what will get x1 plus y2 plus z2 comma x2 plus y1 plus z1. That means x plus y plus z is not equal to x plus y plus z, right? That means the second condition is also not satisfied. Let's say whether the scalar multiplication condition satisfied or not. So if we talk about the scalar multiplication, so we are assuming that there exists a zero vector. There also this unique vector minus x is there, because here we are not any talk about any kind of we didn't we here I did not anything say that there does not exist any zero vector or does not exist that minus x or minus y. These are all existed. Okay, now let's move to the eighth condition. Move to the eighth condition. So says c1 plus c2 multiplied with x. So when I multiplied c1 plus c2 with x, what we will get? We will get according to the multiplication. It is just a minute. So according to the multiplication, this should be the rule that c1 cx should be cx1 comma cx2. That means c1 plus c2. That means this is a another scalar. This should be c1 c2 x1 comma c1 plus c2 x2, right? And the thing is, what is c1x? What is c1x? C1x is c1x1 comma sorry, c1x2, and c2x is c2x1 comma c2x2. Then what is c1x plus c2x? It should be something c1x1 comma c2x2, sorry, c1x2 plus c2x1 comma c2x2. So it should be c1x1 plus c2x2 comma, according to the vector addition rule that I have said in the question, c1x2 plus c2x1. So definitely we can see that c1 plus c2 multiplied with x does not equals to c1x plus c2x. So that means among the eight rule, three rules are not satisfied. So that means the space that is spanned by this x and y vector which satisfy this following multiplication and addition rule is not a vector space, right? So in previously it looked very simple that obviously x plus y should be equals to y plus x, but the thing is in that space how the vector addition defined or how the scalar multiplication defined, this also has to be something that these things are also basically the important things. So that means like we can't, yeah. So so every time we have to check that whether these all things are satisfied or not in that vector space in that space, whether the all the eight rules are satisfied or not, or most importantly there has to be some zero vector, there has to be some negative vector, otherwise this is not a vector space. In that case, if we say, let's say if we ask a question something like that, so which rule are broken if we keep only positive numbers x greater than 0 in, let's say, R? Or rather we can reframe this question in that format: the space spanned by only x greater than 0 that belongs to R is the space spanned by only x greater than 0 belongs to R a vector space? So the answer is no, this is not a vector space. First thing is we do not need to check one by one, because first of all the space, let's say the space spanned by x greater than 0 is, let's say, V. Okay, so in V, if we see, if this is a real line, because I'm considering only one dimensional, because R is real and there is into the power there is only one over there. So if we consider the real line, I'm not considering the zero vector. Okay, so zero is excluded and I'm considering only the positive term. This is the positive, so this is 0. So I'm considering only the positive one, excluding 0. That means 0 vector is not included over here. So definitely the rule 3 does not exist. Rule 4 does not exist. That means there is no negative vector, there is no 0 vector. That means this is not a vector space. Okay. Now move to the, from vector space, move to the subspace. What is subspace? Up to this, up to that point, is everything clear to all of you? Anything, any question regarding vector space or the rules of the vector space? This thing is anything, I think, fine for everyone. So subspace is basically a vector space. It is also a vector space, but here, if V is a vector space, then let's say R, which is a subset of vector space V, is called subspace which follow all the axioms of vector space. Means whatever the rules that applies on vector space, that has to be followed in the subspace, that has to be followed in R as well. So the first thing is, so if this is a vector space V, this is a vector space, let's say V, then there is a small space, I'm calling it R. Okay, and this, everything, every rule that is followed in V, that has to be followed in R, then we call that R is a subspace. Means we know that the can anyone tell me what is the smallest vector space in any space? What is the smallest vector space in any dimension? What is, whether it's a dimension 1, 2, anything? What is the smallest vector space?
Any point?
Not any point. There is a particular point.
Origin?
It's a zero vector. The zero is only a
Yes.
smallest. Zero only is the smallest vector space. Zero. Okay. Someone already put a, yeah, Ravi Shekhar. Yeah. So zero is always is basically the vector space. This is the smallest vector space because all the actions followed over there. Because if you multiply 0 with 0, because 0 vector, there exists only 0 vector. Okay, so if you multiply 0 with 0, you will get 0 plus 0. So if there exists any vector, there is no any third vector, means 0 is also third vector. So this axiom 2 is also followed. This axiom 3 is also followed because 0 is over there. Axiom 4 is also followed. Axiom 5 is also followed because if we multiplied 1 with 0, we will get 0. If we multiply any scalar with 0, we will get 0. So all the axioms are followed, and this is 0 vector is basically the smallest. Zero vector is basically the smallest vector. Other than that, any line, so we know that this is the x1, this is the xy plane. So this is basically the R2 space. So any line passes through the any line passes through 0 is basically subspace. any line passes through 0 is basically a subspace, because if we if we call it L, so L is a subset of R2. Okay, so this is passes through 0, that means 0 vector also included over here, and you will get everything, every action will be followed by this. So any vector that is passes through 0 vector is also a subspace. And also the example of subspace is, let's say R2 is also a subspace of R2. That is very intuitive, right? Similarly, R3 is also a subspace of R3. Similarly, any plane in, if we consider three dimension, so any plane that passes through 0, any plane that passes through 0 is also a subspace. So subspace means it has to follow all the rules that vector space follows. Okay. Now move to the okay, let's say, okay, now move to the column space. Column space, or sometimes call it the image space, sometimes call it the range space. So why it is called image space? Because so why it is called image space? Because if we see that A is a matrix which is multiplied by X, and we'll get another vector, let's say B. Okay, I'm considering that this system has solution. Okay, so basically I have a vector, let's say this is in Rn something, this is some M cross N matrix, and this is in Rn. So I am taking a vector from Rn space. This is, let's say, Rn space. I'm taking a vector from Rn space multiplied with A, and I am getting a vector in Rn space, right? So in Rn space. So I am taking a vector X from Rn space, I am multiplying with A, and I am getting a vector in Rn space. So this is basically a matrix. Matrix is basically a mapping between the two spaces. It takes one vector from one space, and its resultant vector is in the other space. So it is basically a mapping. So that's why this is the image space as well. This column space also called image space. So what is basically column space? So column space are basically the linear combination of all the columns of a matrix. So if a matrix something like A11, A12, A13, I'm just considering a 3 cross 3 matrix. So column space are basically all the linear combination of columns. That means alpha multiplied with A11, A21, A31 plus beta multiplied with A12, A22, A32, and gamma multiplied with A13, A23, A33. So this linear combination is basically called a column space. Okay. So when I'm saying that AX equals to B, okay. So when this equation has a solution, sorry, when this equation has solution, forget about let's say forget about that A is a invertible or not invertible matrix. Forget about that condition. So when this AX equals to B has a solution, so this anyone can say, can anyone try that why when this system have a solution, when we can say that this system have a solution? Okay, so we say that system X, yeah, someone I think
Yeah, if A is invertible, right?
No, I'm not saying anything about the A. A is invertible, non-invertible is not required. Sometimes it's not necessary that all the time A has to be invertible matrix. It's not necessary that the number of variables and number of equation should be same. Okay, it maybe there is a case that the number of variables is bigger than the number of equation, but still we can get a result from that. Okay, so the condition to have this system a solution is basically when this v vector, that v vector in the column space of A, means B belongs to that. I'm saying this is as a column space, this C for column space of A. If B belongs to the column space of A, then this system have solution. Means if B is a linear combination of the columns. Okay. So when I'm saying linear combination, so if something I have a something like this, Ax equals to B, so where A is something like 1 0 4 3 and 2 3. Okay, and x equals to, we can see x equals to basically x1 and x2. So that means B has to be the linear combination of this column. If B is not in the linear combination of the column space, that means the system has no solution. B has to be some multi, because x1 and x2 are basically the scalar term, right? So the linear combination of the columns should be B should be in the column space of A, or should be the linear combination of all the columns of the matrix. So let me give you one short example. So we know that identity matrix. So this is the identity matrix we know in 2 cross 2, right? So the columns of identity matrix, basically we can know that it basically represent the whole space. So columns of identity matrix, we can say that this is V1, this is V2. So V1 is basically 1 0 and V2 is basically 0 1. So using V1 and V2, we can represent any vector in the R2 space. All the vectors in the R2 space, because this is V1, V2 are basically belong to R2. So all the vectors in R2 space can be represented by this V1 and V2. So that's why I'm just giving a short term about this thing. So that's why these are called the basis of R2. I'll talk about the basis later. So these are the basically basis. So now move to that. I'm just moving to the next thing. X equals to 0. How to find out? So this is basically the column space. Now, next thing is null space. So what is null space? Null space is basically it consists of all the solution of Ax equals to 0, right? So the system, if the solution of this system is basically solution of this homogeneous system is basically the null space of A. Null space means we have to find out all the vectors, which gives, it basically takes the vector from Rn space X and put it into a 0 vectors. Null space. This is basically the null space of A. Put it over here, right? So it means, so first of all, the dimension, what would be the dimension of null space? Now I have a matrix called M cross N, and that means I have a vector. This is A, this is X, so I have a vector N cross N, and I will get a zero vector which should be M cross N. So the dimension of null space would be Rn, right? The dimension of null space would be Rn, because I'm multiplying the number of columns. I'm multiplying, because the null space is basically the solution space of x equals to 0. The solution space of x equals to 0 is basically this x, all these x's which multiplied with a and gives the result 0 is basically a null space. So all the x's are the null space which gives this, which basically solve this equation, right? So the dimension of null space is basically Rn, or number of columns. In case of image space, what is image space? When I'm talking about image space, this is A, this is X, and this is B. Okay, so here image dimension of image space would be, or dimension of range space or column space would be M dimension, because we are basically interested of all the linear combination of columns. We are basically interested on all the linear combination of columns, not the linear combination of rows. So number of rows here basically gives the dimension of the image space. So is this thing is clear to everyone, or is there something that you want to discuss? I mean, why the dimension of image space is, or dimension of range space is Rm, and dimension of column null space is Rm? Is it is it clear to everyone?
Sir, again repeat it.
I'm saying that, is it clear to everyone that the dimension of, why the dimension of null space is Rn and dimension of column space or dimension of range space is Rn? Is it clear to everyone?
No, sir. Again.
It's not clear. So null space, in case of null space, we are basically finding out the solution of Ax equals to 0 homogeneous system. So Ax equals to 0 basically is a homogeneous system, right? Ax equals to 0 is basically homogeneous system. So we are basically interested to find out all the x, all the possible values of x, which satisfy this solution, and the space that's spanned by all those x's are basically the null space. Okay, so dimension of x, so x here belongs to, I'm saying, Rn. So dimension of x would be, so dimension of null space would be Rn, sorry, Rn, because here exist all those x vector which satisfy this homogeneous equation. Is it clear?
Yes, sir.
Yeah. Now I'm talking about image space or column space or range space, which is basically Ax equals to B, which is no longer a homogeneous system. This now a non-homogeneous case. Okay. So here we are basically interested of all the linear combination of columns. All the linear combination of columns means, let's say 1, 0, 4, 3, 2, 3. So this is multiplied with x1 and x2, and this is b1 and b2. So we are basically here interested all the resultant vectors, all the dimension of resultant vectors. Sorry, b1, b2, b3. All the dimension of resultant vectors. Understand? So here X is belongs to R2, here B belongs to R3. So when we are basically talking about this non-homogeneous system, so we are basically interested on we are talking about the non-homogeneous system and the image space of that matrix A, we are basically now no longer interested on X. We are basically interested on this vector B. We are no longer interested on X. We are interested on vector B because we are trying to find out the what are the possible B's are there, and is this B vector lies in that space or not. Understood? So let's say this is the range space of A. So there are so many B vectors are there. Let's say one is B, another is B tilde, another is B hat, another is B bar. All the B vectors are there. Now we want to find out that whether this B vector, whatever we are whatever we are given over here, this B vector lies in this range space or not. So that means the dimension of range space should be here is R3 in that particular system. The dimension of range space is R3. It is not R2 because here we are basically interested on resultant vector. But when we are talking about the null space, if this is a null space, so here basically we are interested on all the X. Let's say one is X hat, one is X tilde, one is X bar. All these are the X, which gives a solution Ax equals to 0. So here we are basically interested on all those X's, which gives the solution X equals to 0. So that's why the dimension of null space is Rn, which is basically the number of the columns or the number of the elements in X, and dimension of the image space is Rn, or the number of the rows, or you can say the number of the elements of vector B. Now is it clear to everyone?
Yes, sir.
Yeah. So we will do one example from this thing. Okay. So homogeneous equation. So yeah. So the example is find the solution of the following plane, which is x plus 2y plus 3z equals to 0. So now here you can see I have only one equation and I have three variables. So this is basically 1, 2, 3, and I have three variables. So the null space, the dimension of null space of, let's I'm calling this as a matrix. The null space of dimension of A should be, what would be the null space of dimension of this null space is basically R3, because we have three unknown variables. So if we call this as a capital X vector, so basically our dimension of null space is 3. So we have to find out the solution of the following plane. Okay. So what thing that what is the first thing that we should do, since there is only one row and three columns. So obviously this matrix A has one pivot element, and these two are the free element. These two are the free elements, right? So in that case, the solution would be infinite, because the free element, we can choose free element anything. We can choose free element anything. So let's say, so what would be the solution? The solution would be infinite, but as I talked about basis, right? So we have to find out the basis. Basis means, first, here the two are the here are the two free elements. The first we should take z equals to 0. So if z equals to 0, then what would be the y? What would be the y? 0, 0, 0 is not a condition. 0, 0, 0 is not the solution. It always exists. Null space contain 0, 0, 0 solution. Okay. So we have to find out any non-zero solution. For z equals to 0, if we choose y equals to 1 and sorry, yeah, if we choose y equals to 1 and x equals to -2, we will get one answer, right? So our solution, one solution could be -2, 1, 0. Now, second, now we choose y equals to 0. So if we choose y equals to 0, we can choose z equals to 1 and x equals to -3. So another solution is -3, 0, 1, right? Because we cannot choose anything, any value for x, since x is a pivot element. So we have to choose any value for y and z. Now, what would be the solution? So the solution, so first of all, there exist infinitely many solution. This is the first thing, first conclusion. There exist infinitely many solution. Now, what is the solution? So x would be the combination of these two solution, linear combination of these two solution. One, where alpha 1 comma alpha 2 belongs to any real number. So our solution could be anything. Whatever the value of alpha 1 and alpha 2 you put, you will get the solution. So these two are called bases. Basis means, what is the definition of basis? The actual definition of basis is basically, just a minute. So basis, the actual definition of basis means, first of all, that vectors, those are called bases. We will talk about basis elaborately in the next discussion. In this discussion, I'm just giving a brief idea because already professor have mentioned basis in this course, in this week. So bases are basically are independent, means we cannot produce a basis, one basis vector by this basis vector, because here if we say this, if we call this one is a x1, this one x2, so x1 cannot be produced. X1 is what? This is -2, 1, 0, and x2 is what? This is -3, 0, 1. So x1 cannot be produced by x2 alone. Similarly, x2 cannot be produced by x1 alone, right? You can see that we cannot find, we cannot multiply any, we cannot get x1 by multiply any scalar with x2, right? So that means they are independent. They are independent of each other. And using these two bases, we can span the whole space. Means by linear combination of this alpha x1 plus alpha 2x2, this linear combination, we can span the whole space. Means we can span the whole column space, or we can span the whole null space for this case. For this problem, we can span the whole null space by the linear combination of these two vectors. Okay. And they are exactly in basis vector, their exact amount of vector should be exist. Like if we say another vector over here x3, which is something like -5 1 1. So, and the basis vector is x1. So can we call this is a basis? No, we cannot call this is a basis, because this vector, this is not basis, because this vector is linear combination of x1 and x2, right? So this is not a basis. So basis contain only exact number of vector. That means this set is called basis, where exact number of linear independent vector existed, and by which we can span the whole space. Whatever it is, a column space, it's a null space, is a whole R2 space, is a whole R3 space, or it's the whole Rn dimension space. This is called basis vector. Is it clear to everyone? Yeah.
Yes,
The
sir.
two vector x1, x2 both are in R3, definitely, but they cannot span the whole R3 space. They can only span the null space, because to span the whole R3 space. So here basically null space is basically a subset of R3. Okay. Null space is basically a subset of R3. It's a null space itself is a subspace, because 0 0 0 vector is exists over there, and it follows all the rules that follows in the whole R3. But the basis that we shown over here, this basis cannot span the whole R3 space. Okay. To span the whole R3 space, we have to have another independent vector over there. So in R3 space, the basis of the primary basis, I mean, basis basically is not an unique one. Basis can be anything, but whatever the vectors that you choose for basis should be this 2, 3, or 4, whatever the vector that you choose for basis, they should be linearly independent. They should be independent. They are not dependent on each other. Okay, so basis is not unique. So primary basis, I call it a primary basis of R3 is 1 0 0 0 1 0 and 0 0 1. Okay, this is basically the primary basis. So using this basis vector, you can span whole R3 space. Okay. So last thing that we will talk about. Okay. Now comes to the complete solution. I'm just giving a one example, and then we will discuss this complete solution in the next discussion. Before that, here are the few things that you should know. The first thing is, let's say A is a matrix that belongs to, here only we are basically only talk about the real systems. I mean, there is no complex number exist, but all those things can be applied to the complex system as well. So when I'm writing this R, so that means all the elements are real number. There is no complex number over there. So M cross M. The first thing is, when M equals to N means square matrix, right? Now, if rank of A equals to M equals to N, that means full rank, right? This implies matrix A is invertible, right? Because we have, first of all, we have a square matrix. And second, I'm saying that rank is equals to the number of rows, or which is equals to the number of columns. Means each column or each row has pivot element, right? So rank of a matrix is basically the number of pivot element. So that means each row have has pivot element. That means we get unique solution, right? That means only one solution exists. One solution exists. There is no multiple solution. There is no concept of multiple solution. Okay. Now the second thing is when m is less than n. That means what we call it fat matrix. Number of equations are less than number of variables, or number of rows are less than number of columns, right? So when m less than n, and so maximum rank of this matrix can achieve is m, right? So if rank of matrix A is equals to m, right? That means this is not a full rank matrix. So this is short in height and wide in size, right? So we will get infinitely many solution, right? Second thing is when m is greater than n, that means tall matrix. That means number of variables are less than number of equations, or number of rows are greater than number of columns. Okay, in that case, the maximum rank that a matrix can achieve is n, right? So in that case, we will get either zero solution or one solution. Okay. Now number 4, when whatever the case is, whatever the case is, whether it's a square matrix, fat matrix, or tall matrix, if rank of A is less than m, also rank of A is less than n. So for square matrix, if m and n are equal, so that means the rank of A is less than m. That means the matrix is not full rank. So that means we will not get unique solution. In case of fat matrix, it is maximum rank that can achieve is m, but here I am talking about a rank is less than m. That means we will already get infinite solution. In that case also we will get infinite solution. In case of tall matrix, the maximum rank that can achieve is n, but here I am talking about less than n rank. So either we will get zero solution. In case of tall matrix, if it is equals to n, either we will get zero solution or one solution. But here we will get, if the rank is less than n, then we will get no solution. So all the three cases, considering all these three cases, so finally we get either zero solution or infinitely many solution. So here basically we consider all the square matrix, fat matrix, and tall matrix cases over here in this fourth condition, right? So these are the 4 conditions. Now we talk about, we will do one example on complete solution, and then we'll wrap it up. So in the meantime, if anyone have any question, please ask. So we have a system of equation x plus y plus z. Okay. Just a minute. Just hold on. That is a question. Yeah. Before that, we do another example. We'll do complete solution. And this is also complete solution basically. So you have to find out the condition. Find the on B1, B2, B3. To make the following system solvable, right? What is the following system? The 1, 4, 2, 2, 8, 4, minus 1, minus 4, minus 2. We have x1, x2, x3, and we have b1, b2, b3. So this is basically ax equals to b. So we have to find out the condition on b1, b2, b3 so that we have to find out the condition on b1, b2, b3 so that this whole system is solvable. So based on our knowledge of find reduce and row reduce echelon form, so what we'll do, so first we make an augment matrix A augment B, which is something like that: 1, 2, minus 1, 4, 8, minus 4, 2, 4, minus 2, and here b1, b2, and b3, right? So here we can do one thing. The first row solution we get R2 is basically R2 minus 2R1, yeah, and R3 is basically R3 plus R1. What we'll get? 1, 4, 2. Here B1. This is basically 0, 0, 0, and this is B2 minus 2B1, and this is 0, 0, 0, which is basically B3 plus B1. So to get a solution, what would be the condition? So we have to make this 0 equals to 0, right? So that means B2 minus 2B1 should be 0, and another thing B3 plus B1 equals to 0. So that means B2 should be equals to 2B1, and here B3 should be equals to minus B1. So we have to choose B1 in such a way, we have to choose B3 and B2 in such a way such that it should be equals to minus B1 and 2B1 respectively. So if this condition satisfied, then we can say that this system has a solution. If it is not then we cannot find the solution of a system, right? We have already seen this kind of thing in previous discussion, right? So when basically complete solution, now find come to the complete solution. What is complete solution? Complete solution means we have to find the solution of Ax equals to b, this system equation. Okay. We have example. So it's a 1 3 0 2 0 0 1 4 1 3 1 6. So here x1 x2 x3 x4 equals to 1 6 and 7, right? So first thing is we have to make it augment A augment B, A augment B, right? So 1 0 1 3 0 3 0 1 1 2 4 6, augment with 1 6 7. Okay. So first what I'm trying to do is change R3 minus R1, and what I will get 1 3 0 2, here 1, here 0 0 1 4, here 6, here 0 0 1 4, here R3 minus R1, here 6. Again we want to change R3 again, which is R2 minus R3, and we'll get 1 0 0 3 0 0 0 1 0 2 4 0 and 0, sorry, 1 6 0. Okay. So this is something that we get. So now we have to find the solution. Okay, so how to find the solution? So here is a little bit different. When we say we will find out the solution of complete solution, so when we talk about complete solution, this is basically a combination of solution, particular solution, and null space solution. Okay, so this is basically, so the geometrical picture is something like that. So it's something, let's say this is a null space solution. So what is Ax equals to 0? Ax equals to 0 basically, if we talk about a 2D system, so Ax equals to 0 basically something like that line that passes through 0. And when we say it's like something y is equal to mx plus c, something like that, right? And when we talk about x equals to b, so something which is upwards, okay, something like that. They shifted to, or upward or downward, whatever the thing is shifted to something over here. So this is basically x equals to b, and this is basically, let's say, x equals to 0. Okay, so what is your solution? So the solution should be something like this resultant vector of this null space solution, and here there is a particular solution. So this resultant vector is should be the your actual solution, which is basically the null space solution and particular solution, right? So now we get this kind of scenario, something like 1 0 0 3 0 0 0 1 0 2 4 0, and we'll get 1 6 0, something like that. So how to find the first of all, how to find the particular solution over here? So in case of particular solution, so first of all, you have to find out the pivot elements. Here one, here this two, okay, and here the free variables. Free variables means, so pivot elements means x1 pivot element. Where do we get pivot elements? At column 1 and column 3. So that means x1 and x3 are the pivot elements, and x2 and x4 are the free variables. X1, x3 are the pivot variables, and x2 and x4 are the free variables, right? So this is something like that, because this is multiplied with something like x1, x2, x3, x4. So first column multiplied with x1, right? So x1 multiplied with, sorry, I should move to, so this is something x1 multiplied with this plus x2 multiplied with this plus x3 multiplied with this and plus x4 multiplied with this, right? So here x1 and x3 are the pivot variables, and x2 and x4 are the free variables. So how to find the particular solution? For particular solution xp, we choose free variables to 0. If we put x2 and x4 to 0, then what would be the value? What would be the value so that we get this 160 solution? Now put x3, put this term multiplied with this vector multiplied with x2 equals to 0, and this x4 equals to 0. So what would be the x1? So x1 would be definitely 1, and what would be the x3? X3 would be definitely 6, right? Is it clear to everyone? Am I clear to everyone?
सर x3 equal to 6 केम दिला
x3 equals to 6, right? We say that we choose to find a particular solution, we choose x2 and x4. These two are the free variables. We choose this free variable to 0, and depend on this 0, 0, what would be the value of x1? This x1 should be equals to 1, right? Because x1 multiplied with 1, then x2 multiplied with 3, then x3 multiplied with 0, then x4 multiplied with 2. So now x4, x2 are 0. So these two terms are 0. This term x3, whatever the value of x3 multiplied with 0 gives the 0. So only if we choose x1 equals to 1, we will get 1 over here. The first equation is solved, right? The second case, second equation, whatever these first two terms are 0. So we do not need to consider about these two, x1 and x2. So here x3 multiplied with 1 and x4 multiplied with 4. But here x4 we choose 0. So what will be the value of x3? It should be 6, right? So we will get x1 is 1, x2 0, x3 6, x4 0. Is it okay to everyone?
yes sir
Yeah. So this is basically particular solution. Now, what we talk about the complete solution? Complete solution is basically the combination of particular solution and null space solution. Now we have to find out the null space solution as well. So null space solution means we have to find out this matrix. What is the actual matrix? 1 3 0 2 0 0 1 0 and 1 3 1 6. Right? x1, x2, x3, x4 is equals to 0 0 0. We have to find out ax equals to 0 solution. We have to find out the null space solution. We have already do this kind of row echelon matrix. So I just copy this term only. Okay. So we have
सर a equals to जो second row रो fourth କଲମ ର ପୋଜିସନ ଟା 4 ହବ।
Acha, this one, sorry. So this is my row echelon reduce, or you can say this is basically reduced row echelon form. Now we have to find out the value of x, x1, x2, x3, x4, right? So here, these two are the pivot variables. That means x1 and x3 are the pivot variables, and x2 and x4 are the free variables. So we can choose x1 and x4 anything. So first, what I said, if there is a two variable, first choose one variable, two free variables. So first choose x2 equals to 0 and x4 equals to 1. Second, choose x2 equals to 1 and x4 equals to 0. If there exists only one free variable, then always choose that variable as 1. If there is multiple variables, free variables, so consecutively one variable choose 0, one variable choose 1, and other 2 are 0 or other 3 are 0, in that way. So what is so if first I choose x2 equals to 0. So if x2 equals to 0, so what would be the x1? First case, x2 equals to 0. So let's say first solution s1, x2 is 0. So what would be the x1? What is the x1, x3, and x4? Sorry, in that case, I have to. Oh, no. First, I have to choose x4 equals to 0 because I have to do it backward substitution, right? I have to do the backward substitution. So I have to check first this equation, then this equation. Okay. So I have to choose first x2 equals to 0. Anything could be here. Sorry. My mistake. You can choose anything. So x2 equals to 0 and x4 equals to 1. So we know that x1 multiplied with 1 plus 3x2 plus 0x3 plus 2x4. This should be equals to 0, right? So in that case, I choose x2 equals to 0. So this is 1x1. This term goes to 0. This term goes to 0. We will get x4 equals to 1. So this is 2. This should be equals to 0. So what will be the x1? So x1 should be minus 2, right? So minus 2. Am I right? I think. Yes. Minus 2. Yes. Now from the second equation is 0x1 plus 0x2 plus 1x3 plus 4x4. This is equals to 0. So this is 0, this is 0, and so x3 plus 4. This should be equals to 0. So what will be the value of, because we choose x4 equals to 1 over here. So what will be the value of x3? This is minus 4. This is one solution, right? Another solution, we choose x2 1, x4 0. Okay. So if we choose x2 1 and x4 0, so from here we can do the thing. So this is 3x2. So this term 0, x4 is considered 0. So what is the value? X2 is 1. So x1 plus 3 equals to 0. So what will be the x1? Minus 3, right? So in that case, x1, these two terms 0, x4 is also considered as a 0. So what is the value of x3? It is 0. So these two are the solution. These two are the solution for null space. Let's say alpha 1 minus 2 0 4 minus 4 1 plus alpha 2 minus 3 1 0 0, or rather alpha 1 alpha 2. This is basically x2 and this is basically x4, right? Rather alpha 1.
Sir,
Yes. alpha 1.
So are we finding the number of solution based on the number of independent variables?
Number of null space solution, we are finding out the null space solution based on number of free variables, because
Yeah,
here
three
the free
variables.
variables, right?
Okay.
Because if there are three variables, free variables, so first one free variable choose consider as a one, other two are zeros, then the consecutive way, right? So let's say if there is a x1, x2, x3, these three are the free variables. So first I choose x1 1, then other two 0, then I choose x2 1, other two 0, then I choose x3 1, other two 0, in that way, right?
Yes.
And then this is for null space case, because we are considering x equals 0. So what is the complete solution? Complete solution x is basically the particular solution plus null space solution. So what is particular solution? This is 1060. And what is the null space solution? Linear combination of these two. Right? Linear combination of these two. So this is your basically the particular solution. And what is the alpha value of alpha 1 and alpha 2? Whatever the value of, I mean, this alpha 1 and alpha 2 are basically belongs to R. Whatever you want, you choose, you put the value of alpha 1 and alpha 2, and you will get the solution for X. Okay? So we will get infinitely many solutions. Why we will get infinitely many solutions? Because this is a fat matrix. This is a case of fat matrix, and there's a, and also you can see this is not a full rank matrix. This is not a full row rank matrix, because the rank of a matrix is not 3. The highest rank that this matrix can achieve is 3, but the rank of this matrix is only 2, because there are 2 pivot elements, right? So rank of a matrix is less than m, but this is also a fat matrix. So that means here this condition satisfied. That means we get infinitely many solutions, right? Because whatever the value of alpha and alpha 2 we are choosing over here, we get the solution. And in real number, there are infinite number of alpha and alpha 2 you can choose. Is it okay to everyone?
Sir, in the previous slide,
Previous,
where we were comparing the ranks of the matrices to determine the solutions.
and this one,
Yes, sir.
this,
Yes, sir.
yes.
Sir, when we say we are, I mean, the rank is less than m
Hmm.
and rank is less than n in the
Hmm.
fourth case.
Hmm.
Sir, I'm not getting how are we determining that there will be zero, no solution?
So zero solution will exist in case of square matrix, in case of uh, mm, tall matrix case. So as you can see in this question, here in this question, I'm saying that what would be the condition of B1, B2, and B3 so that the system is solvable. So if you, let's say, if you are given basically a equation something like Ax equals to B, this is basically your system, okay, and that B is not in the column space of A. If B is not it is not lying in the column space of A, so obviously we cannot get any solution. Like if we do the row echelon form here, basically if we do this row echelon form, right? Here we have done this row echelon form. Now we have to consider this 0 equals to 0. This should be satisfied. 0 equals to 0 and something. Let's say if this come out like b1, b2, b3, something like we do not get this term as a 0. So let's say 0 equals to something like 1 over here, or 0 equals to something like 5 over here. So that means 0 equals to 5 is not a solution, right? We
Yes,
all
sir.
So that means that system of equation is inconsistent. That means we do not get any solution. So in that case, this is happen.
Oh, okay, you're saying that there is a possibility that
There is a
may happen.
possibility of zero solution. I'm not saying always we will get zero solution. There is a possibility of zero solution. That's why it's a zero solution or many solution. So in this example, we get many solution because the B that we are consider over here, the B that we are consider over here basically lie in the column space of A. because we know that these are the independent column, right? These two are the independent column, and we get V by, if we call this is V1 and this is V3, so V1 plus 6, V3 will get this V vector, right?
Yes.
So that means B lie in the linear combination of this column space. And these two are the basis vector, because these two column are the basis. These two column are independent, and we can span the column space by using these two basis vector. So that's why these are called bases. So we will talk about basis uh, in broader sense in the next class. I'm just giving you the basic idea what a basis basically is, and how we will find out the complete solution of a system and homogeneous solution. Okay. So I hope this is all about today's class. I hope everyone understand what I'm trying to discuss over here.
Sir, will you be sharing these notes? Or
Yeah.
do we have
This
to
note has
watch
been this note and the lecture videos all will be shared with you. Like if you go to that, if you registered that this course and go to that page, you will see that there is
it? Yes,
a,
sir, the Excel sheet will be mentioned.
yeah, there is a Excel sheet over there. So if you
Yes.
go to the page, there is a problem solving session Jan 2025, and if you click over there, you will see that the click here to view problem solving session, and to click you will get a Excel sheet, YouTube link for each week, and the presentation folder. Like this folder, I will be sharing with you that in Google Drive. That Google Drive link also over there, so you can check this video and this lecture, this presentation anytime.
Thank you, sir.
So
Thank you, sir.
yeah, thank you.
Thank you, sir.
Yeah,
Thank you.
yes, okay.